All right, we're going to take a look at this Raspberry Pi setup. I'm doing the NAND gate with a shell script, which was the last homework. But I'm going to really show the measurement setup for how I measure all these delays and collect a whole bunch of data in order to generate a histogram. So I'm kind of cheating a little bit, although I do not consider it cheating. Here's my wedge. I'm using pins G18, G19 as inputs, and G20 as my NAND gate output. Alright, so I have these block things, a little jumper wire here for the ground. Do you see how I have jumper wires coming out of here to go here? Because this alligator clip, if I try to clip it to this ground pin, notice carefully that that's right next to the 3.3 volt pin. And you know that these clips are not all that protected. It would be really bad if you shorted ground at 3.3 volts. It would probably reboot the Pi, and perhaps worse. That would be bad. So let's not do that. All right, so that's an oscilloscope probe there. And I have these other pin things here. Focus in on it, and these jumpers, one jumper is hooking pin 16 or pin 18 and 19 together. They just jump together, and then I have a scope probe snuck here in a little gap for pin, what is it, 18. So input, the two inputs are going up and down together on purpose. So that is 0, 0 to 1, 1, and then 1, 1 to 0, 0. I say I'm cheating because I don't have a function generator hooked up to these to generate inputs. What I'm doing, and I'll come up here, is this is the setup that I have for my pins. I have, all right, so I have pin 18 is set to an input. Let me get a little, there we go. Pin 18 is an input, and I also turn on the pull up resistor. That's the UP. It has a pull down resistor and a tri-state, and I notice now that I made a mistake. And I'll say that in a second. So 18 is an input and it's a pull up. 19 is also an input, but I do not want pull up. I want that to be TRI, which is tri-state. That's what it's short for. And that means it will just follow whatever's connected to it, which happens to be the, what is it? Pin 18, because I have it physically wired together. So I'm going to change pin 19 to TRI. And so on. And then I also need to change pin 20. Don't know if I needed to do this again, to an output. Great. All right, autofocus is not going so well. So what I'm going to do is I'm going to find my command again in my history. I was playing with some wireless stuff. There we go. All right, autofocus, please. Thank you. So this is a while loop, a forever loop, right on the command line. So I'm going to set GPIO to pull up resistor, sleep for 100 milliseconds, turn on the pull down resistor, sleep for 100 milliseconds, and loop. Well, since there's nothing else hooked to that pin 18 is going to go up, then down, and then up, then down, and up and down, and up and down. That's what I want. It's kind of like a function generator, but without hooking up a function generator. I'm kind of lazy. I didn't want to hook it up, even though I would have had to walk all the way across to get the BNC cable for that. All right, so I'm just going to turn this on. All right, it's a while loop. It's running forever. All right, and we can see that the pin, yellow one, channel 1, is hooked to it. It goes up, and it goes down, and there's a delay. It's a variable delay between up and down. This is running in a multitasking operating system, so these delays are actually part of a non-real-time operating system. It's just part of how it works. All right, looks like it's a little discrete. Okay, let's not look at that anymore. All right, so that's that. Now, we're going to run our NAND script. So here's a script. Here's the bash NAND to run it like that. This is what my script looks like. All right, I'm running it as bash NAND, so I don't need line 1, the shebang line. But I put it there. It's just kind of habit as well. Variables for the inputs, input A and input B. I did not add a variable for the output. It would have been good practice to have pin A, pin B, and then out would be equal to 20 and use a variable reference down in the bottom. Oh well. All right, so this was in my script previously, but then I decided to do the trick with changing the input modes of those pins. So I couldn't do it. They were interacting with each other. Really, in this loop, I just need the loop to read 2 inputs, read 1 into a variable, and I know that this command, because I tried it on the command line, outputs either a 0 or a 1. And we have to do some checking. We have to actually see if it's 0 or 1. We can't check it just the number that way. So if in A is equal to 1 and in B is equal to 1, then write a 0, write a 1. I made the inversion just right here. Saved a little, like 1 line of code. I didn't have to invert or add a not. I just wrote them out in the wrong opposite way and loop there forever. Okay, so I'm going to run this script. I'm going to move my mouse down. There it is. Mouse. Start the script running. And it's running forever. We have 2 infinite loops going on, and this is the wonders of a multitasking operating system. All right, and we can see the processor's pegged. So we got the processor, and it's we're using like 30% of the processor. It's working hard. All right, and this is a little warm. I have heat sinks, by the way. All you have to do is ask for one, and I have one to give out. So here's my oscilloscope setup. Channel 2 is hooked to the output pin. Channel 1 is hooked to the input. And hooked to the oscilloscope here. Channel 1 and channel 2. They're on. Turn this on. Okay, so I see inputs and the outputs going opposite. And the interesting thing here, there's maybe a few interesting things, is I went to this display menu. I pushed display. And then persistence. It says variable persistence. Focus, please. Focus. That's really bad contrast. Oh well. Alright, so in this menu, off is the normal mode. And let me just clear the display for a second. Clear the display, and that's what we normally see. I just want a sense of like how this varies. Wouldn't it be nice to like keep a history on the screen? Oh yeah, that's persistence. If we make it infinite persistence, it's every waveform that was ever drawn on the screen just stays there. And then if you want to clear it, there's a button called Clear Persistence, which just resets the display. I had it set up to variable persistence with 60 seconds. I played with this number, and that was about enough to capture the outliers and get a good sense of the mean and the distribution just by looking at this. So play with your scopes. This one has a bigger variance because we're triggering on the rising edge, and the falling edge is sometime later, and that varies. So it doesn't mean too much. So rising of channel 1 to fall of channel 2 is one delay. The other delay is fall of channel 1, rise of channel 2. You were in 340, you took those labs at the end, you know how to do this. The critical part for what we're going to do next is have these measurements set up and properly working on the screen of the scope first. Alright, so screen of the scope, the rest is it set up, and I'm going to move fast so I don't get dizzy. Alright, so let's go over here. Here's my messy desk. And if you have a tough problem, just look at this picture, and yeah, That's my inspiration. Oh, I went to screensaver again. Hey, there we go. All right. Okay. So we're back into Windows here. I'm going to start up BenchVue. BenchVue. Because the oscilloscopes are hooked up. So we start up BenchVue. Sorry if this is shaky. So on. So here's BenchVue. We go down. I'm going to open up the oscilloscope. It's opening. This is installed on the 166 computers. If it doesn't work, please let me know because it should. Instrument settings, this is what you've seen before, right? It's got the data, it does its thing, and it does its thing. You can change the settings from here. Now we're kind of controlling the scope, getting the data. Screenshots, it's great, isn't it? You can say get current screen, get a screenshot. Okay, this is wonderful. This is pretty much what everybody's used BenchVue for so far. If you just want the data, the trace data, you can get that and dump it to a file. Get current trace, which channels, and so on. That's useful. Then you export it down here in the bottom right. Export. All right, but what we're going to do today is called measurement data log. Because I don't want the waveforms, I just want those measurements. Here we go. So this is kind of set up already. I made a name. Click here, 00 to 11 delays. And it actually does both of them. Include date, include time, include number, just so we don't have to worry about clash of file names. Okay, how do we do? Enter. Okay. Start, when I do the start button, sample period minimum just means take lots of them as fast as you can. And then stop data logging. I'm going to log for exactly 2 minutes, so I have a measure of consistency in my data. My histogram will have a similar number of points in it. And that's good if you've been in Stat 240, so on. Stat 240 always comes back. Scroll down in the bottom, measurement, data log, configuration. And can I move this up? Alright, I can't grab it. So we have to scroll. So we have delay, 1 rise, 2 fall. Delay, 1 rise, 1 fall, 2 rise. These are the numbers. Those are the numbers that came up that I set up on the oscilloscope. You can't do it from this dialog. You have to do it on the front panel of the oscilloscope. That's what I figured out. It took me a little bit to figure that one out. And then I read the documentation. All right. So data log stop. Let's start this. Where is it? Way up in the corner. Start all. Start my instruments. Okay, so it's going. And we can see here, this is my countdown. Here are the actual live numbers, and it's just plotting them for us. Okay. I can grab this. It's kind of like oscilloscope style. And you can see this number down here is changing where my 0 is. I'm going to put my 2 delays in the same spot. Actually, I'm going to put them down in my favorite place. And it starts scrolling. And so on. Horizontal scale, let's do 5 seconds per division. Do you see how it's like pretty clearly the blue one has a bigger mean than the pink one? That's really interesting. I wonder why that is. I really wonder why. Alright, I'm not going to wait for 2 minutes, so I'm going to stop. You don't want to watch it either, so stop. We have this data, and what can we do with it? We can save the data, we can save the instrument state, which I did save the instrument state and is posted to Google Drive. Settings, but I want to do is export. MATLAB, Excel, don't do this, that'd be terrible. CSV can be imported into either Excel or MATLAB, so I'd prefer CSV. I don't want to see this data, but this is for you to analyze. And it's 248 samples, comma separated. This is very good. I've saved this before, so I don't need it. And there we go. Now we have a CSV file of this, which is precisely the data we want. All right. So if you need to log data and your instruments are connected to a computer, please figure out how to do it yourself. Or not do it yourself. Maybe get the computer to do it for you. This allows you to eat lunch. And in fact, allowed me to eat lunch today too. Thanks for watching.